So that's what you get for those two values. And if I write these as coordinate points, um, this is what we'll get. So I'm going to pause the video and we'll take a look at those coordinate points. So these are the coordinate points that you're going to get. And go ahead, pause the video and plot the points. And it looks like this, and you can kind of see the shape happening right here. It says now to estimate how many years before your $2,500 initial investment will double. Well, to double, it would need to be at $5,000. So what would happen is we take and look at where 5,000 is, which is here, and I'd hit kind of where my line is, and then I'd go over this way. Now you can certainly put this equation in your calculator, hit the value button at 5,000. That's obviously going to get you much more accurate. But looking at this, or what it should be, is at a little over 11 and a half years, you will double your money. So in question number 5, it wants us to look at the original function, which is f of x equals ln of x, which is a natural log. So if I rewrite this, this would be y equals log base e of x. And what this would look like would be e to the y power equals x. And again, logarithm. What would happen with this graph is that we would have this asymptote here, and that logarithm would look very similar to any other logarithm. I'd have a point at 1, 0. It would kind of bring the asymptote down towards that vertical asymptote of x equals 0, and it would swoop up like this. Now we could get a little bit more definitive in the sense of that this point right here would be E, which is about 2.7, and it would have a height of 1. So if we wanted to get into that specific, we could, but it kind of gives you that shape. And to solve algebraically for this, we already kind of switched it around, right? So then if I wanted to now switch the x and the y's, it would be e to the x equals y, okay? So e to the x equals y, there's your exponential function. What that would be is, right here at 1 going up to 1e, which is about 2.7, and then swooping around that way. So this would be the inverse of the function right here. In question number 5, it wants us to take a look at the parent function, which is f of x equals ln of x. And then we'll look at the function, the inverse function. But f of x equals ln of x, if we want to think about it again, changing it to exponential form, log base e is the same as natural log of x. And if I switch it around, it's e to the y power equals x. And again, knowing the shape of a logarithm, a couple of things. We know that the asymptote of a logarithm will be a vertical asymptote at 0. We know that it will kind of have that anchor point on the side, which is 1, 0. And if I wanted to get really specific, this coordinate point right here would be e to the 1, which is 2.7. And it swoops down towards that asymptote and then comes back up, kind of extending for forever. So if we're going to analyze this graph, there's a few things that we can say about it. We can say that the domain is from 0 to infinity. We can say that the range is negative infinity to infinity. It's continuous because there's no breaks. And it is increasing, right? So it's continuing and it is increasing. You can see that part of the frown right here, so it's concave down. It has a vertical asymptote, that's x equals 0. We already talked about that. It has an x-intercept, which is at 1, 0. And the other thing we'll kind of analyze about this, as the limit x approaches 0 from the right side, the function will go to negative infinity. So again, what we kind of saw here is as it's going this way, what's happening to the graph? It's going down forever. The other part of this is as the limit x approaches infinity, what happens to the function? Well, as it's going this way, what's happening in the y value? That y value is continuously going up. So it's going to positive infinity. Now, as far as this part goes, where it talks about what is the inverse function, we're halfway there. We have e to the y power equals x. Well, in the inverse function, we simply switch the x and the y. So e to the x equals y. So we switch those around, and that's going to be your inverse function. What that would look like, because it's an exponent, anchor point at 0, 1, asymptote here at y equals 0, and it swoops up like this. And you can kind of see that reflection happening, right, over that y equals x. So again, we're looking at patterns of graphs, this time kind of focusing in on these logarithms. So if we look at this function right here and we think about what's going to happen to this logarithm when I add 1 within the parentheses, hopefully we come to the conclusion that we're going to go left 1 unit. And right here, okay, because it's on the outside, there's going to be a vertical stretch, which has a factor of 2. So think about the normal shape of the logarithm. There's the anchor point, it swoops down like this. Because that is 2, that base right there is 2, there would be 2, 1. We have asymptote and it kind of swoops around. But now what has to happen is I have to move it left 1 unit, and I am multiplying all my y values by 2. So instead of 2, 1, my y value is going to now go from 1 to 2. And over here, where we had maybe a coordinate point of 4, 2, that's going to become a point of 4, 4. It's going to stretch to that height. So I'm going to shift this, kind of making those changes. I'm going to move my asymptote left 1 like we talked about. So moving it left. And because that anchor point is usually 1, 0, I'm moving it left to here. And before it was at 2, 1. I'm going to move it left, but now I'm going to multiply it by 2, so it's going to go here. This 4 point is normally at 2, sorry, 4, 2. Normally it's at 2, 4, 2. Move it left 1, but now multiply that y value by 2. So now it's at 3, 4, and it comes swooping in like this. Okay, so that's what's happening with those shifts. There's that vertical stretch from that 2, and that left goes, or that 1 makes it go left 1. Now, it wants us to write the equation of the inverse function. So I'm going to switch x and y. So now I'm going to say x equals 2 times log of 2 y plus 1. And I'm going to make my way here. So what I'm going to do is divide by 2. X divided by 2 equals log base 2 y plus 1. I'm going to change this to an exponential because now that logarithm's by itself. So it becomes 2 to the x over 2 power equals y plus 1. Now I'm going to subtract the 1. And we're going to get the inverse function to be 2 to the x over 2 power minus 1. So there's that inverse function. Think about what that is. It's normally an exponent, right? So it's to kind of have that swooping graph right here, asymptote at y equals 0, the anchor point there. Think about what happens. This 1 makes it shift down 1 unit. And think about what that half makes it do. It's half within the exponent. So it's a horizontal shift, okay? Or I'm sorry, horizontal stretch. This is a horizontal stretch. And it's a factor of half, which actually means it's multiplying by 2. So it's actually going to multiply all my x values by 2. So when I go to do this, I'm going to move that asymptote down. I'm going to move that asymptote to -1. That anchor point that's usually at 1, 0 is now at 0, 1. Notice how it stayed the same because they're inverses. Okay. And it's going to kind of swoop around this way. Now, again, these are inverses of each other. So if this is 1, 2, the other point will be 2, 1. And if this point is 3, 4, the other one will be 4, 3. So you can kind of see that swooping up over there. Again, if you need help with those kind of points, you can always kind of fall back on a t-chart. So I could go back to a t-chart and plug in, let's say, x for 2, right? 2 over 2 is 1. 2 to the first power is 2, minus 1 is 1. So there's that 2, 1. I could put in 4. 4 divided by 2 is 2. 2 squared is 4, minus 1. That's 3. There's that point. You can kind of see how it reflects right there. All right, on the left box, we're going to do the function. I didn't leave very much room for this. And then over here on the right, what we're going to do is we're going to do the inverse function. All right, so starting with the function, the domain of the red line, that's the original function, was -1 to infinity. Again, it's because we shifted that line over there, so it doesn't start till -1 now. The range is still going to be -infinity to infinity. The limit as x approaches infinity, so as the red line approaches infinity, look what's happening. It's going upward. It is going to approach infinity. As f of x, as x approaches, and actually this should be -1 right here. That's a typo. -1 from the left-hand side. So as it approaches that asymptote, sorry, from the right side. So as it's approaching -1, what's happening? It is going down to -infinity. What's the asymptote? Well, we shifted it to x equals -1. The x-intercept also shifted to 0, 0. And we can see that concavity is concave down. Go ahead and pause the video and fill in the values for the inverse function. Okay, so take a look at that. This should make sense as the domain and range gets switched from the original because remember you're switching the x and y's to find the inverse. Even though we want to find the limit as it approaches -1 over here, we want to find the limit as x approaches -infinity over here. So that one's actually going to switch a little bit. Asymptote, y equals -1. Again, switching the x and the y's. Intercept should be the same here and here because 0 switching 0 is the same and it's concave up.